Welcome. In this video I'm going to show you how you can determine quantiles using Python. This includes quartiles, quintiles, deciles, percentiles, etc. Quantiles is a generic term. If I want, for example, the 5 quantiles, it splits the data into 5 parts, which therefore gives me the quintiles. So each then 20%. For quartiles, I'll split it up into 4, which gives me then 25% each. And it basically then, for example, a first quartile tells me that 25% of all the scores should be equal or lower to the first quartile, and 75% should be higher or equal. Now this video will focus on 20 different methods that are actually out there. I have separate videos on how you can just use my own library, which has a function for these quantiles, which you can just run. I have also another video on if you want to use pandas or numpy simply to do this. But in this video I will show how you can actually create all these different methods. To do that, I'll load in 4 different examples, one with a sample size of 8, one of 9, 10 and 11. And I'll also store these as a dictionary, just so I have some labels. That's going to be useful for later. The sample sizes for each of them might also be useful, so I'll also store those separately. Now there are 2 methods that are actually specifically for quartiles, which are known as the inclusive or exclusive, and the exclusive method. The idea here is if you have the median actually splits the data into 2 sections. So for example, for if I have 8 values, it's 1 to 4, and then the second part is 5 to 8. Or if I have 10, it's 1 to 5 and 6 to 10. But that becomes slightly different if the sample size is an odd number. So for example, for not x10 but x11, do we include the median or not? So I can either include it. So in that case, if we look at the inclusive, I say, well, I include it in the lower half and also in the upper half. And the same for if it's 11, 1 to 6, and then 6 to 11. So these are then nicely split into 2. The exclusive method says no, you just leave out the median. So here the median was 5, so 1 to 4 and 6 to 9, and the median is just left out. The quartiles are then again the median of each of these. So I can simply say, for example, with this one, the median should be 2.5, and the third quartile, so that would then be the first quartile, and the third quartile would then be 7.5. Well, if I have the inclusive method and look at example with sample size 9, then actually the median, the one in the middle, is 7. Now Python has in its statistics library a function median, so we can simply actually run all of this, which splits the data and then looks for the median for that part. So it's the same as before. I haven't imported pandas, which imports pandas as PD. Actually, I only need to run that once, and then you can see all the different variations for the different sample size. So inclusive, exclusive for a sample size of 8, no difference. But if it's an odd number, we do see a difference. Here we also don't see a difference, but here again we do. If you prefer it as a formula, we can write them down like this. The inclusive method, the index of the value would be n plus 2 over 4 if it's an even number. So if the sample size is even, so modulo 2 should equal then 0, and otherwise it's n plus 3 over 4. Similarly, these formulas apply for the third quartile, and if you have the exclusive method, you get these formulas. Alright, but that's just for the quartiles. Actually, even more, those are only exclusively for the quartiles. But you can also use any of the quantile-based methods. And this all starts with how do you determine the index of the value that you are after. So if I want 20%, do I simply say, well, I take the sample size times 20% and that's going to be the value I'm going to be after. That's the most basic version. However, if you then have like 0%, then you get the zeroth index and that doesn't exist. So what some actually do is they say, well, you always add 1 and then you multiply. Or you can use this approach where they say, well, you multiply the 2 and you add a half. Or what Excel is doing, you subtract 1, then you multiply, and then you add 1. Or this Heinemann and Fan, they actually came up with 2 different variations. So there are quite a lot of different, I call them indexing methods. They're not too complicated. I've included them as one small function, so that makes life easier, which takes the sample size as input, then the proportion, and then the method you want to use. This was for the inclusive and the exclusive, and these are all those formulas you saw earlier. So this makes life easy for later on, so we can choose an indexing method. So for example, if the sample size is 8 and we want 25% and the method Excel, then the index should be 2.75. Once we have the index, we're not done. The index is either an integer, so like 1, 2, 3, 4, etc. Or it's not, and that means it's a float, so there's some decimal part. If it's an integer, then usually you simply take that value. So if it says the index should be 2, you take the second value. After, of course, you sorted all the values. But if it's but there's one exception. There's one method that says no. If it's an index, if it's an integer, then you add a half. So you take the midpoint between that index and the next one. So actually you then use as an index the integer plus a half. If the index has a fractional part, so like this 2.75, we could say, well, that's 75% between 2 and 3. So we also take 75% between whatever the value is of 2 and whatever the value is of the third value sorted, after sorting. So that's sometimes referred to as linear interpolation, and you can do that with this looking formula. Now you might notice these brackets, and that's going to be important. If it's like a hook that's going down, then it's the floor function, so basically indicating always round down. And if it's the hook is up, then it's the ceiling function, so it means to always round up. So we can actually do the linear interpolation by this. If it's an integer, we simply just look at that number, and otherwise we fill out this formula by using the floor function and the ceil function that are both available in the math library. So now we have a function for linear interpolation, but besides linear interpolation, we could actually also use a rounding. We can simply round the index if it's not already an integer. There are different ways of rounding. So there is the rounding to the nearest even integer. This is the default method in Python. So 2.5 gets rounded to 2. But 1.5 also gets rounded to 2 because 2 is even and 1.5 is closest to 2 from that perspective. And 2.5, well, if you would round it up, it would be 3. So it's actually 1.5 away from 4, and it's only half away from 2. So they sometimes refer to this, I think, also as banker's rounding. You can also simply always round up or always round down. But the normal rounding is the nearest integer. So I call that normal, but perhaps the banker's rounding is normal, but this will always round 0.5 up. But then of course you could also always round 0.5 down. So I'm using these less than and greater than signs to indicate that kind of rounding. And yet another method is to now use again the midpoint. So you simply round down the fraction and then you add and you round it up and you take the average of that. So As mentioned, Python's core uses the round method, which is the bankers. We can use ceil and floor for ceiling and flooring, so rounding up and rounding down. And for the nearest and half down, well, for the nearest we can simply add a half and then round down. And for the half down, we can actually check if it's ending at a half. If it doesn't, then we can simply use the same as over here. And otherwise, we also use the same over here, but then we subtract one because this will always round half up. And if we then subtract one, it actually rounded it down. So we can have all our different rounding methods. Note that if we're using the interpolation, the linear interpolation, then it doesn't need to round anything. So it simply doesn't round and doesn't do anything, and it simply returns the original one. And then we can finally combine all of this. We have to select the data, which quantile to determine. Then we can select the indexing method. If the index is an integer, do we want to use the midpoint or not? If the index is not an integer and the quantile is below 50%, what do you want to do with the index? So any of those methods over here. And again, if it's above the 50%. So that gives a lot of different options. But we have a function for each of them. So I can make this quick quantile function, which simply says to take in the data, all of the ones of the input that's required. And then it simply goes over all of them and uses the functions we made earlier. So this gives us basically a nice quantile function. Oh, there is an error, roundings. Oh, I haven't actually executed this one. And now it does work. So the different methods I've come across all have different settings for these. So here's a full overview of the name I gave to the method, the indexing it's using, what it's doing if it's an integer. Actually, that's always the same for the lower and the upper versions. In a lower version, if it's a fractional, which might be different from what if it's a upper fractional. So I've actually included all of them as my quantile methods as a dictionary, and now I can use the function and simply run it and get the required quantile. If you want, you can see all the variations by looping over just about everything, and that gives a very long list of 80 rows, so 80 different ones for all of our different samples. Just to check if everything was actually different, I made this bit of code, and this should return are all methods different. Takes a little while because it has to go over all the different options for all the different data sets, and it's checking if it's not equal to another one, but it's not, so all of them are indeed different. Alright, so that's 20 different methods for you to calculate quantiles and quartiles. I hope this video was helpful, and thank you for watching.